Hello guys, today we're going to start the first part of a series of labs we're going to do on dendrochronology. So we've talked about stems a little bit, and now we're going to focus specifically on trees. There is a 5-part series to this lab, and each individual lab has between 3 and 4 parts to it. So I'm going to do my videos in smaller sections. I'm going to take it part by part and piece by piece instead of doing one video for the entire section. So this video will be on part 1 of Lab 1, Launching an Expedition. And I'm going to stop my ambiance here. If you guys are ever interested in finding some background noise that you can work to, I've been getting into ambiances a lot lately, and I found this cozy fall coffee ambiance with relaxing jazz music and rain sounds. I don't know. It keeps me calm whenever I'm doing work, so that may be something that you want to look into as well. All right, so this is what your lab sheet will look like. And you can see it says it's Lab 1 up here at the top, and there is a website. And this is the website that you're going to be using for the entire thing. You'll notice it is split up into sections. You can see part 2 and there's part 3. So I'll have 3 videos for this lab, and each section will have its own link in the main part within Canvas. Somehow I got logged out, of course. And these things happen. So I'm going to go through and look at these questions with you, and I'm going to talk about the answers, and that way you guys can actually, take what I'm saying and you can write down pieces of it. You can summarize it. If I write it on here, then it's going to show up on your Google Doc, and well, then there'd be no point in you doing the assignment because it would already be done. So whenever you click on that link, or if you post it into your browser, it will take you to this page here. And you can see it says Lab 1 here, Launching an Expedition, and there's the different parts to it. So you can click on the individual parts and it should help you to fill it out. There's also Lab 2, 3, 4, and 5. Down here it says Trex Guides. Those are teaching resources. You guys won't have to use those at all. You won't have access to them either. They actually have to approve you as a teacher in order to gain access to that stuff. So you're just focusing on the actual lab sections themselves. So our first part here consists of about 6 questions. And we're going to go through, we'll read everything, we'll watch the videos. So brief history, what is dendrochronology? In the late 1800s and early 1900s, Andrew E. Douglas founded the science of dendrochronology, the technique of dating events, environmental change, and archaeological artifacts by using the characteristic patterns of annual growth rings in timber and tree trunks. As a young astronomer working at a Lowell Observatory in Arizona, Douglas had a particular interest in the sun, especially the cyclic behavior of sunspots and how the sun influences weather. He began looking at the annual growth rings of trees and noticed a relationship between the size of the growth rings and the climate factors, such as moisture and elevation. He plotted the width of the tree rings and compiled the first chronologies to show how trees record climate changes through time. Noting the similarity in the response of trees across the region, he invented a technique that would prove to be a fundamental tool in the tree ring studies, cross-dating, or matching the patterns of tree rings from one to another. This allowed scientists to mark exact calendar dates for each ring. Today, tree ring analysis is not only used to determine what climate was like in the past, it can also be used to date the works of art, like wooden frames, violins, and other wooden instruments in buildings. To see the process of cross-dating in action, watch the historical footage of A. E. Douglas at work. These video clips are pretty short, too.
Tree rings were the first proxy records researched by the scientific community. In the late 19th century, Andrew Ellicott Douglas pioneered the study of tree rings in Flagstaff, Arizona. The
Douglas is a very good observer. He was just a guy who noticed stuff. And he saw these patterns of broad and narrow rings on the ponderosa pine stumps, and he figured that these were characteristic patterns related to the climate conditions of each year. He took that and developed some rather simple but good tools for matching those patterns, for seeing if there's a common pattern. And that's what the scientific use of tree rings is based on. In the late 30s, he persuaded the Arizona Board of Regents to establish the Laboratory of Tree Ring Research as a department of the university. It's on the basis of that it became possible for numerous colleagues in different countries and across different parts of North America to join together to build continental scale networks of tree ring data.
Great. So that was the first part, or the first video, I should say, not the first part. Tree ring basics. Trees typically grow one ring per year. They start growing in the spring. The cells are light tan in color, and they're known as early wood. And as the growing season ends in the fall, the cells will thicken. The cell walls thicken. The dark band or late wood and eventually stop growing in the winter, causing a very distinct ring. The ring pattern that forms over the entire life of the tree reveals the climatic conditions in which the tree grew. Abundant moisture and long growing season result in a wide ring. A dry year may result in a very narrow ring. And we'll look at the diagram. At sites where trees are more sensitive to temperatures, such as high altitude on a mountain or in a boreal forest in the northern Alaska and Canada, then a wide ring indicates a warm year and a narrow ring indicates a cold year. In this activity, you will learn how tree ring science is done. Where do tree ring scientists travel to find suitable trees? What tools are used? What techniques can be used to prepare and analyze tree core samples to reveal the nature of the past climate? So we have to find climate-sensitive trees. Conducting tree ring science isn't as simple as it might appear. The vast majority of trees we see on hikes or while driving have not captured a good climate record over long periods of time. Dendrochronologists need to search for long-lived trees that grow in fairly harsh environments, making them very sensitive to the surrounding conditions, where their growth is slow, so slow that many years will be recorded in their lifetimes. One such tree is the bristlecone pine, which grows in Arizona, Colorado, New Mexico, Utah, Nevada, and eastern California, sometimes under very cold and dry conditions. The oldest known specimen is named, and they're going to have some crazy names in here, Methuselah, and is a 4,765-year-old tree there. You'll have a chance to explore the bristlecone pine site in part 2 of this lab. What characteristics do dendrochronologists look for in research sites that will give them the best chance to reconstruct past climate conditions? Watch the video below and answer the stop and think questions. Okay. So based off of what we have read and what we watched, you should be able to answer these 3 questions, which are coincidentally the same 3 questions that are on our activity guide here. So what types of trees and tree ring sites are most useful for tree ring research? For that, it really depends on what you want to be studying. So I believe they talked a little bit about that stuff in the very first section here. Yeah, he mentions it up here, talking about climate factors such as moisture and elevation. So if you want to study moisture conditions, then the best trees to study are those that are in dry areas with limited precipitation, kind of like the Southwest. The tree ring patterns from these trees are going to be growing in drier regions, and they'll reflect better summer moisture conditions than trees that grow in wet conditions. If you're interested in learning about temperature from tree rings, then scientists would choose research sites that are at high elevation, like a mountaintop, where trees can't grow any higher because it is too cold. Trees from the northern latitudes, like Alaska, Canada, and Siberia, are also sensitive to temperature conditions. Number 2, why are the trees growing in manicured or landscaped areas not useful to study past climate conditions? That answer is actually from the video we just watched. Trees in landscaped areas are watered regularly, and they're typically taken care of because you want your yard to look nice. This practice leads to more or less equal tree ring widths over time, and some scientists call this complacent trees. The result is that the tree rings of these trees are not very sensitive to climate, and thus are not useful for a tree ring researcher to answer any questions about the climate because you're watering them, you might be fertilizing them, so you're helping them to grow. And the last question we need to answer for this particular part, what governs the rate of tree growth at high altitudes? That is going to be temperature. Instead of the amount of available moisture, it'll govern a tree growth at high altitudes. It's all about the temperature. Okay, so there's our first 3 stop and think questions, and now we can move on, and we have 3 more questions to go before we get to part 2. So coring trees. Now let's learn how to obtain tree core samples from a tree. People often ask if drilling into a tree to take a sample from its wood harms it. The core samples that scientists take from trees are actually quite small, less than a diameter of a pencil, and non-destructive to the tree. The tree will heal itself fairly quickly, similar to when a spout is removed after tapping a tree for maple syrup. If there is concern for a particular group of trees, scientists can dip their tree borers into alcohol to be sure they are not spreading any diseases from tree to tree. If forest managers are concerned for a particular forest, they can deny scientists permission to core trees when they apply for a permit. So we're going to watch dendrochronologist Nicole Davy describe how to core a tree. And before I really started looking into dendrochronology, I was not aware that it was just a tiny little sample that was like the size of a pencil or smaller than a pencil. And if we were in class, or if you're in class, I do have some samples of tree cores and what they look like. But they are extremely, extremely small.
Hi everybody, I'm Nicole Davy from Lamont Doherty Earth Observatory's Tree Ring Lab, and I'm going to show you how to core a tree today with your class. And I have an assistant. Want to say something? Hi. This is Augie. He's my assistant today and my son. All right, so one thing to consider when you first come into a site, you want to look around and see what trees are healthy, because you don't want to core a dead or dying tree because your increment borer could easily get stuck. So one of the first things I do is pick a tree that looks like it might be the oldest of the stand. Then I would just walk around the tree, make sure there's no dead branches, make sure there's no big scars that you're going to go into. You want to, find healthy bark, and you want to core right where it's going to be comfortable for you. So right about where you can twist your arms. And then I go straight in between the bark, make it really simple, and we aim for center. All right, so this is an increment borer. You can get this at Forestry Supply. So usually you can get small ones for less than $200. This one's probably around $300. I think it's 16 inches. But we have this nice hollow borer that's got, I don't know if you can see that, but it's threaded and it's super sharp. And it goes right into the handle. And then you have your spoon, which you want to be really careful not to just absentmindedly put on the ground because you could step on it. So you might want to give it and bend it to an assistant to hold. All right, so let me go in here. All right, so then we're going to find a place right in the bark. And I'm looking for center because we want to get to the center, to the pith. And like I said before, you want to be real comfortable where you feel like you can get your most power. Because it actually does take quite a lot of strength. So what I first do is I try and push through the bark. And I use all my weight to push in. And then I slowly and real steady, without moving this core. Thank you, Augie. I just slowly with my palm am pushing it in and letting the threads catch. Now the threads have caught and we can start twisting it in. Nice and steady. And hearing that sound is a good sound. A nice healthy tree. Okay, so we would then sink this at least halfway into the tree to be sure we got center, and you can go all the way in. And I probably wouldn't do, it's okay to do 2 cores per tree, but I wouldn't do more than that. And then we usually do not fill in the hole with anything. If you're particularly concerned about the tree, you could use alcohol for the borer before you put it in. Some people plug it. You can do research and see if that's something you want to do, but it's not something we typically do. Okay, so here we have our spoon. This helps us get the core out, and you can see at the very tip, it has teeth. So, and that will help grab the core. So what we do is we put the spoon in and we try and get under the core. Be careful not to put your weight on it so you don't bend it. And I didn't feel it catch the core, but sometimes you can feel it. And then what we do, got it? Is we back the core, we break the core, so we go back the other way. We start backing it out, just counterclockwise. That's good. And then we start to pull. Go ahead. Real slow, you want to pull it out and hope you get a core. There you go. And very often you can slow down and you can see the rings. This is a tulip tree, so it doesn't have super clear ring boundaries. You can see them pretty good there. But then you have a straw with you. I didn't bring a straw, but you'd stick it right into a straw to protect it, and then you could label it, whatever you decide to name your site. Your core, you want to pretty quickly start getting the core out, because you don't want it to get stuck. Because they can very often get stuck, especially if you're coring targets. So what we do is we bring a Sharpie marker and we actually mark the core, and we make sure that it's backing out. And if it's just spinning, you really need to put your weight into it and pull it out. You twist it real slow, but you put weight behind it, so it'll twist out.
All right, so I don't know about you guys. I'm not particularly fond of the noise that comes from coring a tree, but it seems like a pretty simple process, although I'd imagine that if you are coring a hardwood tree and it gets stuck, then you might be a little bit concerned simply because that little borer is like, a small one is around $200? Oh my gosh, so expensive. But I guess it's easier than cutting down an entire tree to see how the weather was looking for the past couple of years. Processing the cores. So scientists collect core samples from 20 or more trees at each of their sites. These samples need to be carefully contained and brought into the laboratory for analysis. Cores taken from a tree need to be mounted in a special wooden holder or core mount and then finely sanded to bring out the ring pattern more clearly. So this is what those ring patterns would look like. And you can see, I mean, there's some really wide rings. There are some extremely tiny ones. These ones were taken from spruce trees in Alaska. They've been placed in wooden core mounts and finely sanded so that the cell detail is visible under a microscope. Each ring represents 1 year of growth. The wide rings indicate good growing conditions, warmer summers in this case. Tree ring patterns are then studied with a number of different scientific instruments. The buttons below will take you to the Lamont Doherty Earth Observatory Tree Ring Lab in Palisades, New York. These images are 360, so you can look around, zoom in and out, zoom in to both the main work area and the core room so you can see what's on the tables and the walls. And then we'll finish off these questions here. So for number 4, why is one part of the tree ring light in color and the other part dark in color? We actually probably could have answered this question with our last set. So the light part of the ring is called early wood, and it starts to form in the spring and has large cells with thin walls. Toward the end of the growing season in the late summer and fall, the cell walls thicken, making the walls look darker. This is called the late wood. The early wood and the late wood come together to form the tree ring. What factors did Dr. Davy consider in choosing a good tree to core at her location in the woods? So this was from the video. She stressed the importance of not coring dead or dying trees so that as not to get your tree ring borer stuck. She also explained that it is best to core a tree at a position that is most comfortable to you, about chest height, so you have the most power. She also suggested that you place your borer between the ridges in the bark to get started, and you want to aim for the center of the tree. Okay, so now we need to go to the tree ring lab. To answer question number 6, we're looking for what instruments did you see in your tour of the Lamont Tree Ring Lab? So this is what the lab looks like, and I don't expect you guys to do any research into finding out what these instruments are. I just want you to write down what you see. So for example, here's a computer, so I would put that down. And I also see what looks to be some type of a microscope. Oh, okay, so that must be outside of the lab. Oh boy. Here we go. There's a big machine over here as well. I'm not really sure what that one is, so I would just say that it's a couple of unknown, very large instruments. There is some type of a microwave back in there. Maybe they use that for something. We can go to the tree ring core room as well. And here you can see that there are tons of boxes with core samples, and it also looks like they have a actual huge piece of bark that is labeled for something as well. So basically you're putting down microscopes, computers, a microwave, and some very large unknown instruments. And that is it for part 1 of this lab. I'll see you back here again for part 2.